Good morning, everyone. I have a very serious question for you. Do you enjoy Hacktivity so far? Yes. Okay. So now let's try it with more enthusiasm. So, do you enjoy Hacktivity? Yes. Yes. Okay. Great. I'm very happy to hear that. First, I want to tell you some public announcement. There will be another very great presentation at the other conference room, and that is one of the most anticipated talks I wanted to watch, but unfortunately I cannot be there at the moment, but I'm really sure that it will be a very good presentation. It has already been presented at Black Hat and DEF CON, and I can assure you that it's also a very good one. So my name is Zoltan Balazs, and I have a lot of certifications, and I'm really into offensive researches. For example, I am the developer of the zombie browser toolkit. I also developed some kernel drivers which you can use to bypass hardware firewalls. I also developed a malware which you can use to test malware analysis sandboxes. And last but not least, I have played with some very crappy IoT devices. So what I'm going to talk about today is that I will introduce you to elliptic curve Diffie-Hellman cryptography and my project codenamed Iron Squirrel. I will tell you what I think my attacker model is, and I want to explain why I believe that this is something different or new what you have seen before. I will talk about the cat and mouse game of defense and offense, and I want to invite you for a little game. Whenever you find cyber on the slides, just shout it. No, not this one. Good try, but not this one. Just shout it and you will win a hacker beer. Okay, so I think behind every offensive research there is a story, and I also have my story. I had a discussion with next generation or so-called breach detection vendors, and they told me that the network appliance cannot be bypassed with any exploits and stuff like that, and I told them that I am sure that it is possible to bypass them, and they told me it is impossible. And what happens when someone tells me that something is impossible? I go home and I start to code. So this is how it all began. Why you should listen to this talk? How many of you guys are an exploit broker, like working for Zeridium, or are working for law enforcement, like FBI or stuff like that? Okay, one guy, very good. How many of you guys penetration testers or red team members? Hands up. Okay, a little bit more. And how many of you guys are in blue teaming or doing forensic investigations or do some exploit kit research? Okay, a little bit more. So I think all of you can find some interesting bits in my presentation. But if you are neither of those, I think learning about elliptic curve cryptography is always fun. Okay, so first let's start with the introduction, and I'm going to tell you about what are the exploit kits and how targeted 0 days looks like, what is the Diffie-Hellman key agreement, what is the difference of the elliptic curve-based Diffie-Hellman key agreement, and what is this encrypted browser exploit delivery, and how my idea was implemented by the bad guys. Okay, so an exploit kit is basically a tool or a software which exploits your browser. Pretty straightforward. What happens if you use a 0-day exploit in your exploit kit, but you lose it? By losing it, I mean that it is leaked out, some researcher finds it, reverses your 0-day, sends the 0 day to the vendor and it gets patched. It means that you lose a lot of money, right? Because it's not a 0 day anymore. Everyone can download the patch for it. There were multiple cases, but I want to tell two very important cases about losing 0 days. The first one was when Ahmed Mansour was targeted with an iOS Safari 0 day exploit. And at the time when this happened, I think the price for such a 0 day exploit was something between like 100,000 US dollars or 1.5 million US dollars, which is a pretty lot of money if you lose this. Unfortunately, Ahmed Mansour is still in prison, which is pretty bad. I really do hope that the government of his will change his mind. We will see. Another famous example of losing 0 days was when probably the FBI was targeting some pedophiles, and what they did that they were able to install code on a Tor Onion site which was used by pedophiles. And what happened here that someone who was visiting this site noticed the 0 day exploit. He copy-pasted the code from the website, put it in the Tor browser forum list, and the 0 day was patched in like 2 days. So it was not a 0 day anymore. And the problem with this that after this, the FBI couldn't catch so many bad guys because it was not a 0 day anymore. Okay, how many of you learned about Diffie-Hellman key agreement and how this works? Okay, that's pretty good. I have found this very nice representation of Diffie-Hellman key agreement on Wikipedia, and it says that, let's say that Alice and Bob, they want to agree on a common secret color. And what they can do, that first they both choose same color, which is publicly known that they will use this, which is the yellow one. And meanwhile, they will choose a secret color. Both of them will pick a random color and they won't tell anyone what this color is. After this, they will mix the secret color with the common shared secret color, and they will use a public transportation to exchange these colors. And let's assume for a moment that subtracting colors, it's a very hard thing to do. It is hard for me, for sure, but let's just say that it is hard for everyone. And whenever they receive the secret colors from the secret color mixed with the common color, they can use this color to mix it with their secret color, and they will have a common secret, which is the same on both sides, which is really great because they have used public transportation, and it doesn't matter how many people can see this, but they still have the common secret. If we are talking about modular-based arithmetics, it looks like a clock where the actual values are jumping basically randomly on the clock. Yeah, this is just a very simple, basic explanation how this works, but we are talking about very, very huge numbers when it really comes to cryptography. So it is very hard to get the secret, to calculate the secrets from all the publicly available information, but it is really easy to calculate the common secret once you generated your part. The difference with elliptic curve-based Diffie-Hellman key cryptography is that elliptic curve math is a lot faster than the traditional Diffie-Hellman. I did some tests, and it looks like that it is at least 5 or 10 times faster on the same hardware than it is Diffie-Hellman key agreement. And the problem with the traditional Diffie-Hellman key agreement is that it is painfully slow when it comes to JavaScript, which you will see why it's important. And basically, this is how elliptic curve-based Diffie-Hellman looks like, that you have some very strange curves, and you define some mathematical formulas, how you can basically add two numbers together. And I think a very good representation how this works is like a billiard pool table, that whenever you see how the billiard pool table looks like, you have no idea how this state was reached. But whenever you pull a ball and it gets to a single point on the table, it's trivially easy to calculate that if you pull the ball with this force in this direction, that it will end up here. So now that everyone knows how elliptic curve Diffie-Hellman works, let me introduce you to my project, which I will talk very deeply in this presentation. Let's say that there is a client on the left side, which I, as an attacker, want to attack. The first step in this attack is that the client browses with his browser for a content. It can be the only thing I need, that this content he browses has to be controlled by me. Whenever my server as an attacker receives a GET request, first I will generate all the elliptic curve Diffie-Hellman keys on the server part. Then I will send all the crypto libraries and elliptic curve Diffie-Hellman parameters to the client in JavaScript. So now, in the fourth step, the client can generate its own elliptic curve Diffie-Hellman secret keys. And now that it already has the public key from the server, it can generate basically the shared secret as well. In the fifth step, the client has to send its public key to the attacker server. So now in the sixth step, the attacker server can also calculate the same common shared secret. And now what the attacker I can do is that I can basically encrypt the whole exploit with AES or something different, with a very good and trusted symmetric encryption, and deliver the exploit in this encrypted fashion to the client browser. Because the client browser already has the same shared secret as it was used by the server to encrypt this traffic, it is able to decrypt the JavaScript content and run it in memory. And because it's a 0-day, the browser is vulnerable to this JavaScript exploit code. So the exploit code will run on the victim browser. And for example, if it's a shellcode to initiate some malware download, then it can reach out to the exploit server to download some malware. And now because they have some shared secret, it can be also done in an encrypted fashion. And because of this, the malware which gets delivered to the victim browser, it's also encrypted. So this is the whole idea I have created. But I think a quick demo will show you better what I'm really talking about. So here you can see that for Chrome, I have only used a very basic JavaScript alert message because I didn't have any useful exploits for Chrome. So here you can see that an alert message was popped up. But let's see what is the document object model of this web page. Here you can see some encrypted blobs. And here is another one. And you cannot see the alert text, right? Because it's totally encrypted. But let's just copy this JavaScript code and let's try to reverse engineer what it is. So we put this code. Yeah, here you can see that in the network traffic, the very same encrypted stuff was sent, so I'm not cheating. So here we can see that from the JavaScript console, it is possible to decrypt the code what was delivered, right? But it is only possible because the common shared secret was left in the memory and it was never deleted, which I will do in a later phase of this presentation. Okay, so how did I implement it, my idea? Actually, it's already a 2 years old story, and my first idea was to implement this in Node.js. I chose Node.js because it was very cool that I can use the same crypto libraries on the client side and in the server side. How many of you have implemented anything in Node.js? Okay, that's cool. So it was my very first Hello World project, just to play with Node.js itself, and I was able to implement my idea in 1 or 2 days or something like that. After a while, I realized that this technique is very useful, so it would be very nice to integrate it with Metasploit, but Metasploit was written in Ruby and not Node.js, so I tried to port it to Ruby, and it was very funny because it took me basically more than 1 week because I had to create a compatible crypto library in JavaScript and in Ruby, and it is really a pain. But finally, I managed to do this. And I tested this implementation with multiple browsers, and it is compatible with the Edge browser, IE 11. Unfortunately, IE 10 or older IE versions are not supported because they are not compatible with the crypto libraries. It is compatible with Firefox or the Tor browser, Chrome, Opera, Mobile Safari, Mobile Chrome, Android built-in browser. So basically any modern supported browser is compatible with this Iron Squirrel encrypted exploit delivery. And when I created my first Node.js proof of concept, I was very proud about this, so I tweeted about this. And as I mentioned in the story how I started this project, my main focus was on bypassing perimeter network defenses. And I think my tweet was it had a really huge success because I got 3 retweets and 3 likes. Yay! But after some months, something very strange happened. FireEye came up with an analysis that they have found basically the same technique implemented in the Angular exploit kit. There were some differences in the implementation. First of all, because they were targeting old IE browsers, they were not able to use the elliptic curve cryptography, and also they were not interested in hiding the exploit code itself. They were only interested in hiding the shell code. But still, I think that it might be not a coincidence that I came up with this idea, I published it, and 2 months later, the bad guys implement it. So what can you do whenever you are faced with a very challenging cryptography problem? Yeah, you use math, right? So this is what happened here, that the Kaspersky team, they have found some very clever mathematical way they were able to basically factorize all the secret keys which was implemented by the bad guys. This was possible because the bad guys had to use Diffie-Hellman encryption, and because generating very long keys takes a lot of time, and it's impossible to use it in a browser exploit scenario. They had to use shorter keys, which were susceptible to factorization. One strange thing that Angler exploit kit is basically dead nowadays. The reason for this is because most of the guys are behind bar, and which is very, very good. I think Kaspersky's active participation helped putting these guys behind bar, but there is another exploit kit which was active still recently and doing this Diffie-Hellman key encryption. So I believe this is how the Angular developers felt when they discovered that the Diffie-Hellman keys can be factorized. Right? Okay, so now let's talk about what I believe my attacker model is, who is my attacker, and I will talk about the reverse engineer and what a reverse engineer can do with this encrypted exploit delivery, what can a next-gen breach detection system do, and what are the capabilities of these attackers. So please keep in mind that I am the attacker by doing these exploits, but for me, the reverse engineer is the attacker. Okay. So first of all, any reverse engineer can record any network traffic. Yeah, this is pretty easy, and they can replay it. For example, at the beginning, I have mentioned you the iOS Safari zero-day exploit. As far as I know, the Citizen Lab, when they reverse engineered this exploit, they have used basically this kind of technique to reverse engineer the whole traffic. They were able to do a TCP dump or similar on the network traffic, so they were able to record it, and when it was recorded, it was easy to analyze. Also, a reverse engineer, because he has access to the browser, he can use some debugging in the browser itself, or also if the reverse engineer is hardcore enough, he can use some assembly-based debuggers to debug really in a very deep level. It is important to note that assembly-based debugging might not be available to the reverse engineer every time, because let's say we are testing with a very new iOS iPhone or something like that, and if there is no jailbreak to that iPhone, there is no way to do this assembly-based debugging. Let's see what a reverse engineer can see whenever he records all the traffic, and what can he see. He will see some crypto libraries which are used also in legitimate projects. He can see some public key exchange and some encrypted blobs. And because he's basically in the middle and he doesn't have access to the browser itself, he has no idea what the shared secret is. And without the shared secret, he won't be able to guess the correct key, which can be used to decrypt the encrypted exploit, right? Why do I think this is different or a new technique? In the past, there were many techniques which protected the exploit code, but it was mostly some kind of obfuscation, or even whenever encryption was used, it was encrypted in a way where the encryption key was sent together in the clear with the encrypted text. So it's for a reverse engineer, it is trivially easy to decrypt all the traffic. Now it's totally different because the reverse engineer doesn't have this encryption key. And you might think that, okay, this is very similar to SSL or TLS, so why is this really new? When it comes to SSL TLS, if you are the reverse engineer, then you can control the client. And what this means, that you can install any root certificate in the client browser store, you can man in the middle the TLS or the SSL connection, and from this point you have access to the whole clear traffic. So it is trivially easy to inspect. Right? How many of you used any proxy and used this technique to man in the middle SSL connections? Okay, that's really cool. Okay, so let's see what a reverse engineer can do with traditional browser exploit forensics. In the past, it was a very nice way to reverse engineer exploit kits by doing some so-called exploit replay. What exploit replay really means that whenever you record the whole exploit traffic, you can replay it in a reproducible way. So whenever you debug it and you screw it or something happens, you can rerun it as many times as you want. And it is also the same with SSL TLS, that whenever you can man in the middle this connection, the SSL TLS connection, you can replay it anytime. But with the Iron Squirrel exploit, you cannot replay it because the browser client, every time it runs, it will generate a totally different public and private key. So the shared secret for it will be totally different. And if you try this exploit replay, the client will send a totally different public key HTTP request to the server, which the replay server won't be able to understand because it's a different traffic, what it expects. But if the replay server tries to send back this to the client, the encryption will just break. I'm sure that it is hard to understand this, so that's why I have created a video for this. So here you can see the browser, which I'm using common Metasploit exploit. Here you can see that PowerShell started with the exploit, and this started code execution by popping up a notepad. This is one of the best tools if you want to replay any HTTP traffic. It's called the Fiddler proxy, and it has this autoresponder module. On the left, what you can see is all the traffic which passed through the proxy, and on the right, you can see that I have copied the traffic from the left to the right. So whenever this kind of request is made to this proxy, it will answer the exact same content. So now this is not an encrypted exploit. So if I click again on this exploit, it will run. And if we go back to the Fiddler, based on the background blue color, you can see that this traffic was served by the proxy itself. So it was a replayed traffic. Okay, now let's see what happens if I visit the encrypted exploit delivery site. the exploit will work the same way it worked before. And here you can see all the requests. The first ones are the crypto libraries I already mentioned. Then you can see that the client public key is sent to the server. Then the server sends back the encrypted exploit, and that's all. Now let's copy all of these requests to the autoresponder, and let's see if we can rerun this exploit or not. As you can see, nothing happens, and the whole chain broke in this step because Fiddler had a different request which it was told to replay, but the victim browser generated a totally different public key, so now Fiddler doesn't know how to handle this request. Of course, we can hack the Fiddler autoresponder a bit and tell Fiddler that, okay, I'm not interested in this exact request, but let's say that if any public key is sent to me, just serve this traffic. So let's try this again. IE is a bit stupid, so we have to rerun the exploit. And here we can see some very cryptic crypto messages. What this really means that I have no idea how to decrypt the traffic which was sent to me because I have some totally different keys in the memory. So as you can see, with this traditional exploit replay, it's not possible to reverse engineer and replay the exploit anymore, which is pretty cool. I think. How many of you guys are Archer fans? Good, very good. So I really do believe that this encrypted exploit delivery is something totally awesome, like Archer does always. But it's not only me who's saying that this exploit replay is broken. For example, if you check this Trend Micro blog, they have blogged about this, that whenever they try to analyze the Astrum exploit kit, which used, again, this Diffie-Hellman key encrypted exploit delivery, they were not able to replay it. And there was some very fun fact in this article, which is the Astrum exploit kit developers, they didn't use 0 days. They have used exploits which were already patched, but the exploit code was never in public. It was basically only used by them. And because they have protected their exploit code with this Diffie-Hellman encryption, none of the other exploit kit developers were able to reverse engineer the exploit code, so they couldn't steal their exploit code. So it's pretty fun how some encryption can basically break the reversing, not for the good guys, but for the bad guys as well. So let's play a little bit of defense and offense here. I will talk about what you can do to prevent or detect this kind of attacks on the network level, how you can analyze it still on the endpoint, and after that I will tell you some ways from the attacker's point of view, what you can do to make the endpoint analysis a lot harder. So one of the best improvements you have to make whenever you deliver your exploits is to use one-time URLs, which means that every exploit URL is delivered only once. This is not my idea. For example, in the hacking team exploit kit, they have used the same, that because they were using targeting single people, they could generate unique URLs for every target, and after the request was served, they can shut it down to prevent any further analysis. If we are thinking about the FBI use case, whenever they target all the visitors of a website, I think this idea can still be implemented. What the FBI has to do is to basically check that only serve the exploit for users who are already logged in to the forum, which I think is already a good idea. And after that, they can deliver the exploit to one user once. Sorry. I already implemented this in my code. You can also use some time limits in your code. So if there are significant delays between the requests, then you can be sure that someone is actively debugging it. So you just don't serve any more traffic to this. It is always a good idea to remove the full document object model from the browser after the exploit runs, which is also implemented. And let me show you how my idea works with the Tor browser exploit I already mentioned in the beginning. So here you can see Wireshark is empty. This is the vulnerable Tor browser. I visit the exploit delivery site, and here you can see the encrypted blocks, but now because the exploit is running, the whole browser just hangs and it doesn't respond at all. And when it's done, it's totally empty. You cannot see anything on the DOM side. Sure, you can still see what was on the wire, but again, this is just the encrypted blocks. Okay, so let's try the same trick I have used with the Chrome alert window at the beginning. Let's copy back here and let's try to decrypt it. But as we can see, we got back something very strange, and the reason for this because my JavaScript code was already deleting or overwriting the shared secret in the memory, so it's not possible to decrypt this traffic anymore. It was running only once in the memory. Meanwhile, you can see that the exploit was successful and how this FBI exploit worked, that it contacted single web server with a fixed URL, and the host name was basically the computer name where the exploit was running, and the cookie was the MAC address of the computer which was exploited. So here you can see that it's only encrypted and you cannot reverse engineer it. You cannot replay it. So it's already gone. So if you see this and you post it on the Tor forum, no one can help you to fix the bug. Okay, so what can you do on the network level to prevent this kind of attacks? You might try to detect encrypted traffic, but I'm sure that if you try to implement this, it will lead to a lot of false positives. You might try to do some non-iron squirrel specific protections, like blocking uncategorized or new domains, or use domain whitelisting. I'm not sure if there are any users here who have domain whitelisting in their corporate environment, but I know that it is a very pain to administer. If you are an attacker, you can do a lot of things to still improve your attack. For example, if someone has implemented domain whitelisting, then you can still hack one of the whitelisted domains and use this in a watering hole attack. Or if you are the NSA or GCHQ, hands up? No one? Okay. Then you can use the quantum insert techniques, which is a very nice and awesome man-in-the-middle technique. But there are still ways how you can analyze the encrypted exploit delivery on the endpoint. One trick can be that somehow you log or log the shared key or the client private key while it's in the memory, or somehow you fix the random number generator so the client will generate the same private keys every time it runs, or you can just somehow hook the JavaScript code, or if you are debugging iOS, then you might use some remote debugging in iOS Safari, or you can create some detailed JavaScript execution trace log. And last year, there was a very awesome presentation here at Hacktivity presented by Miklós Desbordes-Korchev, who has seen that presentation. All right. So I have used his project, and it was basically the only solution I knew of which was able to practically reverse engineer my encrypted exploit delivery. So let's see this in action. So let's start the module, which was created by Miklós, and it hooks the IE browser, and it will basically hook the eval and document write calls in IE. So when I visit the exploit site, the exploit ran, but here I can see the whole exploit code in clear text, which is very nice. And how I was able to do that is that at some point in time, the exploit code has to be in clear text in memory. And this project does exactly the same. Whenever it's in clear text and in memory, it will just write out to you and log it. So it's pretty nice. From an attacker point of view, you can still do a lot of things like detect the debug window, which I didn't care to implement. If you are an attacker, you should do very proper fingerprinting on the exploit before you deliver it. You can use a hell of a lot of code obfuscation, which can help prevent man-in-the-middle attacks, because Diffie-Hellman and encrypted elliptic curve Diffie-Hellman doesn't do authentication. You can still man-in-the-middle it if you know the exact protocol and you know the exact syntax, how it's used. But if you obfuscate it differently every time you deliver, then it's impossible to man-in-the-middle it. What I have done, that I generate multiple Diffie-Hellman keys in my project in a row. And if the output is the same, then I know that I'm in a debugging environment, so I can just stop execution. You can also bloat your project and add a whole lot of junk code, which can help reverse engineering make it a lot harder. And as I have mentioned, the project from Miklós, it hooks eval and document write calls at the moment. But it turns out that JavaScript is awesome, and there are like 40 other calls which you can use to do the exact same stuff, like with eval. So if you really want to monitor this kind of traffic, then you have to improve Miklós project and hook on the 40 calls. When I started playing with it. I implemented the document right, and it took me like 4 hours to find how to hook this, so it's not a trivial task. So what are the conclusions of the reverse engineer who tries to attack my exploit code? For sure, any determined reverse engineer can restore the exploit from a memory dump, or there can be tricky ways to basically stop the whole exploit execution whenever any exploit-related system call is going on. But I am 100% sure that whenever someone uses encrypted exploit delivery, it can delay the analysis or the discovery of the exploit by days, weeks, or even months, which is always very cool for the attackers. Okay, got it. And actually, I have made a limited edition cyber beer just for this conference. So after the presentation, you can get that one as well, besides the hacker beer. I think I don't have time for this slide, so I will just skip this. Yeah, I tried to implement it into Metasploit, but turned out that if you are not a core Metasploit developer, it's very hard to do. So if any core Metasploit developer is here, contact me. I need your help. I think the conclusion of this whole talk is that at the moment perimeter security is dying, and with all the mobile devices and encryption trends, perimeter security is becoming less and less effective. So the conclusion of this project is that if the attackers have used my Iron Squirrel project, they could have prevented definitely the leak of the iOS Safari 0-day, and this is also true for the Tor browser 0-day. If you as an attacker use one-time URLs, you can make reverse engineering a whole real nightmare, but you have to know that Iron Squirrel is not about bypassing endpoint protection, so it doesn't deal with EMAT or stuff like that. But one thing is for sure, if you deliver 0-day exploits for any targets, then OPSEC is very important. There are some ethical dilemmas which I'm pretty happy to discuss with anyone, like why am I helping the bad guys, or who are the bad guys? I think it's a very, very complex project. But the main question we have to ask ourselves, if we don't defend ourselves against these kind of attacks, then what happens, right? So that's all, folks. Thank you for your attention.